Hey, good afternoon. It's time to start. Any questions from our lecture last time on Wednesday last week? So for those of you who were not here, I already posted the exam grades for the second exam. So those are available online. And if you have questions about your exam, or if you have questions about the way it was graded, you have until Wednesday to discuss those with me. So you can connect to my office hours. I have office hours tomorrow from 8:30 to 10:30, virtual office hours. Or you can set up an appointment with me at a different time. So make sure that you reach out to me. If you don't remember from our first lecture this semester, I give you a week to discuss any questions that you have about the exam. What I want to avoid is to, at the end of the semester, you try to, I don't know, find out what happened on the first or second exam, and then that time is too late. So the time is now. If you have questions about the second exam, better connect with me tomorrow or set up an appointment. Okay. So today we are going to continue our discussion on the material handling equipment, specifically on designing conveyors. So on our first lecture, we look at a specific type of conveyors. Today we're going to look at another type of models for representing the operation of these material handling equipment. So I'm going to start this lecture going over or basically reviewing what we did on Wednesday, and then we're going to transition to the new concepts. And this is all part of the first objective for this class, which is to develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. And on the lecture from Wednesday, we look at conveyor loops with deterministic loading and unloading sequences. Today, we're gonna look at the stochastic scenario in which we're gonna look at conveyor loop with Poisson arrivals, meaning that we don't know specifically when these arrivals are gonna happen. So we're gonna model those using a Poisson process. For the first type of conveyor, which is the one that we discussed on Wednesday, we were knowing for sure how many arrivals we were getting at any time period. So the learning objectives for this lecture 10, is to learn models for specific type of conveyors and also to understand the basic procedures for calculating horsepower or speed requirements for power belt and rotor conveyors. So let's look at what we did on Wednesday. We were looking at these conveyor loops with deterministic loading and load loading sequences. And this is the type of model that we study, in which we have specific number of stations located around the conveyor belt, which is represented by this line. And then we have the little black dots representing the carriers for the conveyor. And the idea is knowing in each station where you're gonna get a loaded part or an unloading process. Also knowing the number of carriers that you have in the conveyor. We wanted to estimate or basically compute the capacity of these carriers. So how many parts each one of these carriers must have, must carry. How much space you should have in each one of these carriers. So the schematic representation, again, here we have S up to S minus 1 conveyors, carts or carriers. And then the conveyor is in the middle, is rotating in this counterclockwise direction. And the stations are named or basically numbered in a clockwise direction. So there are S stations located around the conveyor, numbered in reverse sequence to the rotation of the conveyor. Each station can perform loading and or unloading. And there are K carriers equally spaced around the conveyor, and the passage of a carrier by a workstation establishes the increment of time used to define material loading and unloading sequences. So we went through this notation. We established that we were gonna use station 1 as a reference point for defining time. And consequently, the carrier N becomes carrier N plus K after passing through that station that we are setting up as the origin for our analysis. In this case, station 1. So carrier N becomes N plus K immediately after passing this station 1. The sequence of points in time in which a carrier passes station 1 is denoted by Tn, where Tn is the time at which the carrier N passes station 1. Okay, so we are also keeping track of that T or time. And the amount of material or number of items loaded on carrier N as it passes station I is denoted by Fi of N right here, for I equals 1 up to S. And the amount of material carried by carrier N immediately after passing station I is denoted by HI. Each carrier may hold multiple items. So again, the idea is for us, knowing that this is the setup, knowing the sequence of loading and unloading, knowing the number of carriers that we have in the conveyor, to estimate how much space we need in each one of these carts. So I went through explanation of these equations. So essentially what we are trying to do is to set up an iterative process in which we are going to take into account the series of movements that are happening in each one of these stations. And then based on a sequence of movements that we believe we're going to reach steady state, based on those movements, we are going to estimate the space for these carriers or carriers. So in analyzing the conveyor, it is convenient to employ the following relation. So we are going to do the summation of all the Fi, which again are assumed to be periodic with the period P. And we're going to look at that information in order to estimate these numbers. So additionally, this equation is representing the flow balance. So this is basically stating that everything that goes into the conveyor will be unloaded at some point. So using these three equations, we obtain the following results. K over P cannot be an integer for steady state operation. So we're gonna look at those numbers. P is the period, K is the number of carriers, and then letting R equals K mod P, R divided by P must be a proper fraction for general sequences of F1N to be accommodated. And then we also explained what this mod operator was. So we were looking basically at the residual of a division of two numbers. And also we established the material balance equation for carrier N. And then in order to determine the values of this equation, the following approach is taken. So here's where we go through this iterative process of understanding every time you go through this station, this is the amount of gonna be loaded, unloaded, and this is the resulting value for the flow. So after computing these HI values, then we compute the C value, which is used to compute or to find the desired solution for HIN. And at the end, we use all the values for HIN to compute the maximum. And that value B is what tells us the maximum capacity or the minimum capacity for these carriers. So we went through this example. Here we only have two stations. One is a loading station. The second one is an unloading station. And again, this is the deterministic case in which we know for sure what will be the number of items that are going to be loaded to the conveyor and the number of items that are going to be unloaded. Again, loading happens in the first station, unloading happens in the second station. So we have a situation involving a single loading station and a single unloading station. The conveyor has 9 carriers, equally spaced. And what we need to do is to determine the required capacity per carrier. The loading and unloading sequence occurs with a period of P equals 7 and are given as the following. So this F1 of N is telling us that we're going to load one item first in the first car, another item on the next car, and then 2 items, 2 items, 2 items, and then back to 1 and 1. This second value or set is telling us that we are not going to unload anything until we get to the 6th period, in which we're going to unload 5, and then again 5. So that will, if you look at the summation of this, should be 10. This is also minus 10. So F1 plus F2 is equal to 0. So everything that is loaded is also unloaded. In this, we have to compute F1, and we do that by looking at the difference between F1 and F2. So 1 minus 0 is 1, 1 minus 0 is 1, and so on, till we get to 1 plus 0 is 1, 1 plus 0 is 1, till we get to 1 plus minus 5, so that's minus 4. 1 plus minus 5 is also minus 4. And we also look for the R value. So we have K mod P, 9 carriers, 7 period. So that's going to be equal to 2. Given that 9 over 7 is not an integer and R over P is 2 over 7, which is a proper fraction. It's a prime number. So this tells us that we can find a solution for this problem. So going back to the explanation, recall that the amount of material carried by carrier N immediately after passing this first station is denoted by HI of N. So that's what's going to keep track of the amount of material carried by that carrier. And in order for us to find a solution or a sequence, we need to find an initial solution for the problem. So typically what we do is to set up the initial solution to 0. Okay, so we arbitrarily let H1 star of 1 equal to 0. And then we use that, basically stating that we start with 0 in our cards. And then we employ this relation in order to find the rest of the sequences. So for H1 star of N, we are going to employ the following relation. So as I stated in our previous lecture, what's going to happen is we're going to use this initial solution, and we're going to plug in that into this piece of the equation, H1 star N minus R. Okay, so that initial piece is gonna help us find the next value. And that first piece is arbitrarily selected, meaning that we are making that equal to 0. So just to get an initial solution so we can get the iterative process started. So we are making H star 1 star of 1 equal to 0. So what that means is I need to find the next one, which is this value, and I'm gonna plug in this value here. So that means that n minus r has to be equal to 1, because that's the value that I have. And to make that happen, I know r is equal to 2 based on this computation. So for this expression, this is 2, I know that. For this expression to be equal to 1, then n has to be equal to 3. So that tells me that the next h star that I'm going to find is going to belong to h of 3. So h1 star of 3 minus 2, which is equal to 1, plus f of 3 equals h1 star of 3. So for me to be able to use this value into this equation, I need to find what the value of n is. That n is going to be 3. So that means that the next sequence that I'm going to find will be for 3. I'm going to use f of 3. F of n is 3. h1 star of n equals 3. h1 star of n minus r is 3 minus 2. So this is 3, this is 2. I can use 1 here, and I have the value of 1. So this expression then will become h1 star of 3 plus h1 star of 1 plus f1 of 3. That's equal to 0, which is this value, plus f of 1 of 3, which we already found is 1, 2, 3 equals 2. So this is equal to 0 plus 2 equals 2. So my h1 star of 3 equals 2. And now I have two values. I have the value of h1 star of 1, and I have the value of h1 star of 3. And I have to repeat this process in order to find all 7 values of h1 star, which is what we are doing here. So for the next one, I'm sorry, this is the one that we just found. So I'm going to use h1 star of 3 to find h1 star of 5. So I'm plugging in h1 3 here using the value for 5, f of 1 of 5. So if I go back here, f1 of 5 is 1, 2, 3, 4, 5 is 2. So 2 plus 2 is equal to 4. So I have the value of h1 star of 5. And now I can use that to find the h1 star of 7, which is 0. And then after that, the next one will be h1 star of 9. But since our period goes up to 7, then the sequence is restarted. Right? So h1 star of 9 basically is telling you you got up to 7, and now you have to restart it. So you will go up to 2. 7, 1, 2. So the next value that you're going to find is for h1 star of 2. And that's what I found here. Next is going to be h1 star of 4, h1 star of 6, and that will complete the values for all 7 periods. So once I got all these numbers, here's the set 0, 1, 2, 3, 4, minus 1, and 0. Now I can find the values for h star of 2, which is going to be the difference between h1 star of n minus f1 of n. I have f1 of n here. identify that set is given. So I'm going to subtract that set from this one, and this is the resulting set for H2 star of n. Okay, so those are the two sets that I need to find the C value. So I need this set and this set. And the next step is to find the minimum for H1 star of I. So the minimum between those two sets is this value, -2. So that's the minimum. And now, for I equals 2 and n equals 6, consequently, the sequence H1s of n are given by this. So if we go back to this, is the equation that I'm using to find. So once I find Z, the desired solution is given in terms of HI, not the star. I'm going to use the star values minus Z to find the sets of HIs. So if we go back here, there's going to be 0 minus -2 equals 2. 1 minus -2 equals 3. 2 minus -2 equals 4. 3 minus -2 equals 5, and so on. Then for this one, 1 minus -2 equals +1. 0 minus -2 equals 2. 0 minus -2 equals 2, and so on. So using that number, I'm able to find these two sets. And then the last step is to find the maximum among this set. Yes.
I'm sorry.
For this set? For this? For this?
No, I'm sorry. The one.
This one? Yeah, sure. Yeah, so what I'm subtracting in order to get those, that's a good question. Going back to this part right here, what I'm doing is I'm going to subtract HI star n minus C. So essentially what I'm doing, I take every value from here. So let's start with this one is 0 minus -2. So 0 minus -2 equals 2. So that's this value. And then you repeat the process. Good question. So at this point, we're basically at the end of the process. B is going to be the maximum from these two sets. So the maximum is 6. So essentially what this is saying, if you look at every possible sequence for this conveyor, the maximum number of items that you're going to have at any point is going to be 6. Okay, so looking at the flow of these cards for 7 periods, the maximum number of parts that you're going to have in a card will be 6. So based on that, we make the conclusion that you need at least 6 spaces in each card for this conveyor. Therefore, each carrier must have sufficient capacity to accommodate
iPad's in there, just careful.
6 items. I can hear some of you in the Zoom, so please mute your mic. Okay, so location of stations and contents of carriers, 2 stations. Consider a conveyor system with 1 loading station and 1 unloading station. The loading and unloading sequences are this ones. If there are 7 carriers on the conveyors, then R equals 2. Solving this sequence, again, going through the same process, will give you this final number of cars. So you see, now that we have reduced, So for this example, the capacity for the cars will be equal to 5. But in this example, again, you have one loading and one unloading station, but the sequence and the number of items that are loaded per time period is different. So also, you only have 7 carriers. So if you perform all the computations that we just did, you will end up looking at this set of values, and a maximum from this set will be equal to 5. I have another example here I want to show you. And I'm going to make this one available also. So in this example, we have the same conveyor, the same sequence of loading and unloading. But the only difference now is that we have 10 carriers equally spaced. So in the previous example, we have 9. In this one, we have 10. The loading and unloading sequences occur with a period of P equals 7. So the question is, again, would this change the capacity that you need for your carts or your carriers? So in this example, I generated the information using, well, I typed the solution. So you will see it. I went through the same process of identifying the H1, HI star for 1 equals 0, and then we employ the same relationship. So I was able to find the following. I start with H1 of 4, then H1 of 7, and I continue that process until I'm able to find all of them. So I have here H1 start of 6, H1 start of 2, and H1 start of 5. So my H1 star end set is equal to 0, minus 3, 0, 2, minus 1, minus 4, and 2, and minus 2. Then using this set, I was able to find the H2 star by subtracting that H1 star and minus F of 1n. Then find the minimum of HI stars, and then computing the H1 star, H1 and H2 sets. Have those values here. Then the rest will be to find the maximum among these two sets. In this case, B equals 7. So the reason I'm presenting this example is that you can see for the previous example, the capacity here with 9 carriers, we're seeing that we only need space for 6 items per carrier. But if you add an additional carrier to your conveyor, you will think that you might need less space, but that's not necessarily true. Again, it will depend on the sequence of loading and unloading. So that's what we did in the other example. We added an additional carrier, and the result is telling us, no, if you do that, you're gonna have to add more space to your carts or to your carriers. So, and that's why we need to do this type of analysis carefully, because your intuition might not tell you what really happens. Okay, so even though you added an additional car, you might think, okay, if I add more cars, I need less space, but that's not what's happening in this example. You added an additional cart. However, you still see that most of those sequences are low. Maximum is 5, but at some point you have 7. For the rest, you have some zeros, you have 1s, you have 3s, up to 5. You don't have any 6, but here at this point, you end up with 7. So that's gonna affect your capacity in terms of how many cars or how much capacity you need in each one of these carriers. Okay, so again, all this we discussed in our previous lecture. I wanted to go back to it just to make sure that at least review that. Again, something that you might not get at the beginning. You will have to go check these numbers on your own in order to get this very well. So practice this example, practice the next the example that I'm gonna post on Microsoft Word. And if you have questions, we can also go back to this on our next lecture. But now we're gonna transition to a different scenario. Before we get into that, still on the deterministic loading and non-loading sequences. So the example illustrates the effect of HIN of the location of the station served by the closed loop recirculating conveyor. Not only can the capacity requirement for a carrier be affected by the number of carriers on the conveyor, but it also can be affected by the location of the stations around the conveyor. So on this next model, we're going to look at conveyors with Poisson arrivals. So again, the idea now is we're going to add some uncertainty in terms of when these arrivals are going to happen. On the first couple of examples, we were assuming that we knew that for sure. We knew how many arrivals we were going to have and so on. Now we're going to assume that those arrivals have some uncertainty. So the number of parts or the timing of these parts can be random. So also concerned with the performance of a closed loop unidirectional recirculating conveyor with stations located around it. Okay, so now we are looking at conveyor loop with Poisson arrivals. So we are also looking at this type of conveyors, closed loop unidirectional recirculating. However, in this case, each station is either a loading or an unloading station, and no station performs both types of operation. Also, there is an input-output queue for each loading, unloading station. And as opposed to following a deterministic pattern, items at loading station I are placed one at a time in the input queue of station I according to an independent Poisson process with rate lambda I greater than 0. And the conveyor consists of equal size windows. Each window holds at most one item. So various conveyors such as the trolley conveyor, in which we are gonna model carrier will be equal to a window, the tilt tray conveyor, and the cross belt conveyors fit this second model that we are gonna discuss. So the conveyor has a user-specified constant length and speed. The length is expressed in number of windows, and the speed is measured in the number of windows passing by a fixed point per unit time. Okay, so basically what we are counting as a window is, for example, how many boxes can we fit in a specific length of the conveyor. And this is the notation for this model. We have Pij, the probability that an item arriving at loading station I needs to be delivered to unloading station J. Okay, so that's the probability of, if we have 4 stations, what is the probability that this item will be arriving to one of the other 2 stations. Fij is the flow rate from station I to J. So Fij is going to be equal to this lambda rate I times Pij, which is the probability that an item arriving at loading station I needs to be delivered to unloading station J. Suppose that there are M loading and N O loading stations. We have theta, which is the set of loading stations. We have gamma, denote the set of all unloading stations. And this lambda denote the rate at which the conveyor delivers loads to the output queue at unloading station J. So for the conservation of flow, we must have this summation of lambda equal to the summation of capital lambda J. So to derive the stability condition, the conveyor loop is divided into K segments denoted by S1, S2, up to Sk, where K is going to be equal to N plus N. Okay, so for example, is a segment could be something like this Si, which is containing all these windows between these two stations. So this could be representing one of those sets or segment. So segment Si will have all those windows between these two stations. Okay, so as shown in this figure, Si, where I equals 1 up to K, represent a set of windows on the conveyor between station I minus 1, which is this one, and station I. By definition, each segment Si ends with a loading or unloading station. Okay, so they're gonna end with a loading or unloading station. Delta I denote the required flow rate, items per unit time or time unit in conveyor segment Si. And by definition, that delta is going to be equal to this double summation of FKL times ZKL. So we have defined Fij. We have to talk about Z. So Z is going to be a binary variable. So as we mentioned already, FKL is the flow rate from loading station K to unloading station L, and CKL equals 1 if the load from station K to L travels through segment Si and 0 otherwise. So if that load is going to travel through this segment, we're going to make that decision variable equal to 1. If that item is not going to travel through that segment, then we're going to make that decision variable 0. V denote the speed of the conveyor, and QI denote the ratio of the required flow rate in segment I to the speed of the conveyor, So that's going to be equal to delta I divided by V. In terms of what have been found in practice and also in research, has established that if we have a lambda divided by the velocity minus delta I, if that ratio is less than 1 or has to be less than 1, is necessary and sufficient condition for loading station I to be stable. What that means is, in steady state, each item arriving at the input queue of station I will be eventually placed on the conveyor if the above inequality is satisfied. This inequality is also can be rewritten as follows. So lambda I plus delta I divided by this speed less than 1. This is defined as the stability factor for loading station I or SFI. Hence, the conveyor loop is stable if and only if this ratio is less than 1 for all i's is theta. That is, if and only if this condition is satisfied. Okay, so using this information, we're gonna look at this example. Here we have, we want to determine the minimum required conveyor speed. Want to know how fast this conveyor needs to go in order to meet this stability condition. See, the speed is right here. So we want to determine what will be the speed so our conveyor can operate in this stable condition. Okay, so that's the goal of this problem, determining the minimum required conveyor speed. So we're gonna have a closed loop unidirectional conveyor loop with 52 windows. And those are listed here. So we start here, and this is the last window. 4 stations are located around the conveyor. So those are here, 1, 2, 3, and 4. Stations 2 and 4 are loading stations. So you can see the arrow going in this direction. That means that this is a loading station. So this is loading. And this is also a loading station. And while stations 1 and 3 are unloading stations, so you can also see that here with the flow. So this is unloading. So 2 loading and 2 unloading stations. And we can define sets, these 2 sets, theta as the loading stations, and then this gamma 1, 3 for the unloading stations. Now we have the lambda values, so the arrivals. Suppose that lambda 2 equals 30 items per minute. So lambda 2 will be for this loading station equals 30 items a minute. And lambda 4 equals 20 items a minute. Now we have the probabilities that if it is loaded in, let's say 2, that this item will get to station 1 for unloading. That is what this means. So P21 is the probability that you will start here, the highlighter, you will start here and you will end up here. This conveyor turns in a clockwise direction. So this goes this way. So we are basically saying, sorry, it's not right. That the probability of 1 or 2-1, what this is saying is that this conveyor for that part will, there's a 60% chance that this part will go all the way here and is gonna be unloaded here. That is what the P21 means. 60% chance that you're gonna go in that direction and you're gonna be unloaded in station 1. P23 is 40%, which means that you're gonna start, you have a 40% chance that you will start here and you're gonna be unloaded here. Okay, and you can see why this Z decision variable 1 or 0 will come into place, because if you just go from 2 to 3, you are not touching every single window, or you're not using the whole conveyor. Same thing for that yellow line. You see, you're not using that last segment of the conveyor. So that gives us an understanding of what part of the conveyors are you going to be using if you're getting from this station to this other station. So P41 equals 0.25. So that's basically looking at this loading station up to 1. So this P41, and then P43, that you're gonna go all the way from 4 to 3. So you're gonna go from here up to here. And those are the probabilities. P21, 60%, P23, 40%, P41, 0.25, P43 is the complement, 0.75. Assuming the conveyor turns in a clockwise direction, determine the minimum speed required in windows per minute to ensure that the conveyor loop is stable. Okay, so that's what we're gonna do next. So we're going to start with computing the flow rate to from station I to station J. So if we go back to this definition, Fij is going to be equal to lambda I times Pij. Okay, so we're going to multiply the lambdas times the probabilities to find the Fij values. So F21 will be equal to the rate from 2, which is 30 items, times the probability that you go to station 1, which is 0.6. So this is equal to 80. F of 2, 3 equals 30 times the probability that you go to 3.4. So this should be 12. F of 4, 1 equals lambda 20 times the probability from 4 to 1 is 0.25. That is 5. And then F of 4, 3 equals 20 times 0.75. So that is equal to 50. Okay, so now I have the float rates from station I to station J. With the clockwise rotation, the 4 segments on the conveyor are defined as follows. So if you remember, every set or every segment needs to end with a loading or unloading station. Okay, so that's what we're going to use to define these sets. So for example, my first set, use a highlighter. go from here and will end up in that unloading station. My second set will start here, and it will go up to here. Third set will go up to here. So it ends always in a loading or unloading station. And then the last one, go from here, and it will end on this in here. Okay, so my first set, S1, will have windows 1, 2, up to 10, 11. S2 will start in 12, 13, up to 27, 28. S3 we start in 29, 30, up to 34 and 35. And S4 will start in 36, 37. It will go up to 52. Okay, so I have 4 segments on this conveyor, and that is defined based on the location of each one of these loading and unloading stations. So I define S1 or segment 1 from 1 to 11, it ends on this unloading station. Then from 13 to 28, it is ending on this loading station. From 29 to 35, ending in this unloading station. And then from 36 to 52, it is ending on this loading station. Okay, so the 2 segments that end with a loading station are segments 2 and 4. So loading stations. Okay, so this is segment 2, and this is segment 4. So those are the ones ending in the loading station. Given the above Fij values for segment 2 and 4, we can compute delta I, the required flow rate, items per unit, time unit in conveyor segment is I. So delta 2 is going to be equal to the summations for all K's and L's of FKL times ZKL. So what we're going to do here is we're going to look at the flow that is happening between these 2 in these segments. Okay, so if I look at segment 2, the flow rate from which goes in this direction. I equals 2, and the flow between K and L that would be segment 2. It's this one. So you will have 18. And delta 4 is going to be equal to 18. So that's coming from here and here. So what's coming from 2 will be unloaded in 1. So that will be 18. I'm sorry, 2 unloaded in 3 will be equal to 15. And for 4, it's going to be loaded in 4 and unloaded in 1. That'll be equal to 18. Yes, so these are coming from this expression. And if you, let's go back here. Okay, so let's go back to the description. Okay, Z equals 1 if the load from station K to L travels through segment SI and 0 otherwise. Okay, so we can do this for every segment. And you'll see how that looks in a minute. So SZKL is going to be equal to 1 only if you have a load traveling from K to L. Okay, so if you saw that expression has an FKL, which is the flow rate from loading station K to unloading station L. Okay, so let us look at this expression. So we are gonna have for K, we have F2, 1, which is we have a flow between F2, 1, and let's compute delta for 2. So we have F2, 1, Z 2, 1. Plus F2, 3 times Z2, 3 plus F4, 1 times Z4, 1 plus F4, 3 times Z4, 3. Okay, so I'm expanding this equation. I'm using the values for the F2, 1s, F2, 3, F4, 1, F4, 3. Those are the flows that we established at the beginning. So this expression basically is going to look at which ones of these flows are passing through segment 2. Segment 2 is this segment here of the conveyor. Goes in blue. Okay, so let's look at 2, 1. So if you go from 2 to 1, are you using this segment blue? The answer is no, right? Because you don't have to pass through that piece. You're getting loaded. Actually, you are, because you're touching Well, no, you're going this direction and you are getting unloaded. So Z21 is 0 because you are not using that segment. 2, 3, you're going from this point to this point. So this Z value is also 0. 4 to 1, you're going from here to here. This is also 0. And 4 to 3, you're getting from here to here. So in this case, this is equal to 1. So in that case, we are going to have 15 times 1. So for the other pieces, we have F21, 18 times 0, plus F23 is 12 times 0, plus F241 is 5 times 0. And that's how you get this 15 number. You're gonna have to look at the all the flows, right? And then you are looking at whether or not you're using segment 2. The only piece that is using segment 2 is when you have a flow between station 4 and it goes to unloading station 3. That's the only case in which you're gonna use that segment blue in the conveyor, because you have to get here, go all the way here up to here. So that's the only piece or the only flow that is touching that blue segment. Blue? Oh yes, because we are focusing only in segment 2. Delta is for segment 2. Okay? So we are focusing only on segment 2. We can do this for segment 1, segment 2, segment 3, segment 4. If we do it for segment 1, let's do segment 1. This is gonna be equal to F21 times Z21. Actually, I don't have to rewrite the equation. It's gonna be the same equation. And actually, we don't have to do it for 1 because 1 is an unloading station. We are only interested in the stations that are loading and then getting to an unloading station. So the only stations that are loading into the conveyors are 2 and 4. So we focus on those 2 because the other 2 are not loading anything to the conveyor. They're just unloading. So we can do 2 and we can do 4. Let's do 4. So lambda 4. So now we are focusing on this piece of the conveyor, the orange piece. So we have 18 times from 2 to 1, we are using this piece. Yes, we go from 2 to 1. So yes, we are using that orange piece. So we'll multiply this by 1. Plus 12, 2 to 3. If we go from 2 to 3, we are not using that orange segment. We're just going from here to here. So this is 0. From 4 to 1, so this is 4 and then 1. So you are not using yellow. I'm sorry, you're not using the orange. So this is 0. And then the last one is from 4 to 3. So you go from 4, this is 4, up to 3. So you go all the way here, up to here. This is also 0. So it's 15 times 0. So this is equal to 18. So delta 2 is 15, delta 4 is 18. For 1 and 3, we don't have to analyze that because those are unloading stations. They're not loading into the conveyor. So I found the values delta 2 and delta 4 using this information. Remember that the conveyor loop is stable if and only if this ratio is less than 1. So what that means is that we need V greater than lambda I plus delta I. For, in this case, for I equals 2 and 4. So we obtain the following. We obtain V lambda I for has to be lambda 2 plus delta 2, which is equal to 30 plus 15. So this is 45. And B has to be greater than lambda 4 plus delta 4, which is 20 plus 18, which is equal to 38. So this is for I equals 4, and this is for I equals 2. So from these two, we find the largest value. So in this case, that's 45. So hence, the conveyor speed must be greater than 45 windows per minute. And that's the conclusion. For this setup, we want to identify what will be the minimum or the speed that we will need in order to keep this loading and unloading stable. So the requirement is that this ratio is less than 1, or we can solve for B. That means that the velocity has to be greater than lambda I plus delta I. So we compute those values for the speed for station 2 and 4, 45 and 38. To choose the highest speed, which is 45, and the conveyor speed must be greater than 45 windows per minute. Okay, and that concludes our discussion for today. So you have an assignment based on this discussion. So make sure that you look at that starting today. It's due next week. Let me know if you have questions on Wednesday. If you have any questions now, you have time to answer questions. If not, then I'll see you Wednesday.